Here we're going to discuss some logarithmic applications. So the first one we're going to talk about is what's called the pH of a substance. And in chemistry, the pH is defined to be equal to the negative of the logarithm of this quantity. This is called the hydrogen ion concentration of some substance. Your chemistry instructor will talk to you about what it is, but in a lot of problems, you measure that and then you want to find the pH. So let's go ahead and do that now. So for example, find the pH of lemon juice, which has a hydrogen ion concentration of 5.0 times 10 to the negative third. This is called molarity, and it's moles per liter. So this is just a measure of the hydrogen ion concentration. These are the units. So the way we're going to find the pH is use this definition. The pH is equal to the negative of the log, and here we're given the hydrogen ion concentration. Well, let's just write it first here. So it's the negative of the log of the hydrogen ion concentration. So in this case, the pH is the negative of the log. And what is our hydrogen ion concentration? It's 5.0 times 10 to the negative third. So we're taking the log of 5.0 times 10 to the negative third. Okay, and you don't want to put the units in here. So the question is, how do you evaluate this? What we're going to do is, because it's the log of a product, that means we have a property that can take the log of a product to the sum of two logs. So remember, we have this property that, let's write it up here maybe, the log of AB is equal to the log of A plus the log of B. And we can use that here. So it's the log of this plus the log of that, and don't forget the negative on the outside. So it's going to be negative the log of 5 plus the log of 10 to the negative third. Okay, so the negative's on the outside. Now what's the log of 5? On your calculator, we find that to be about 0.699. That's the first part. And then plus, now the question is, what is the log of 10 to the negative third? This is a common logarithm. The base is 10, and therefore the bases cancel out. And the log of 10 to the negative third is just therefore negative 3. So it's plus negative 3. And then when we add these together, we get negative of, adding those two together, it's going to be negative 2.301. And then we take the negative of that to get just 2.301 as our answer. So that's the pH of lemon juice. Now it turns out that the lower this number, that means the more acidic it is, but it's also the larger the hydrogen ion, the larger the hydrogen ion concentration, the lower this number. And you can see why, because, for example, let's say that was 10 to the negative 7. Well, what would happen? The log of 10 to the negative 7 is just negative 7, and the negative of that. So you'd get just positive 7. So if this was 10 to the negative 7, the pH would be positive 7. In other words, if this is small, the pH is large. And if this is small, if this is large, the pH is small. So that's how the pH system works. So now other problems can ask us to, instead of finding the pH, other problems could ask us to find the hydrogen ion concentration. Let's go ahead and do that now. So for example, find the hydrogen ion concentration if the pH is 6.5. Again, we use the same definition. The pH is equal to the negative of log of the hydrogen ion concentration. So the pH is given, right? 6.5. So 6.5 is there. And then we want to solve this equation for the hydrogen ion concentration. Now, to solve this logarithmic equation, we've got to get the log by itself. So we first have to divide by negative 1. Right? This is negative 1 multiplied by that. So these would become, that would cancel, right, with that. And the left-hand side would be negative 6.5. And then that's equal to log of the hydrogen ion concentration. And now we can solve this logarithmic equation by converting it to an exponential equation. So you take the base and you raise it to the other side. So it's going to be 10 to the negative 6.5 is equal to this. That is 10 to the negative 6.5 is equal to the hydrogen ion concentration. And that would be our answer. Now, of course, you want to put the units in there. The units would be molarity, so it would be, or moles per liter. So you could put a big M after that, but the quantitative value is 10 to the negative 6.5. That would be your answer. Okay, so there's another place where we see logarithms, and that would be in the Richter scale for earthquakes. Let's see an example of that now. So first of all, the Richter scale measures the magnitude of the earthquake. So this is what a scientist might report, oh, that the earthquake had a magnitude of 7 or 8 or something like that. But what we are really sensitive to is the amount of shaking. So here, this is the definition of the magnitude that a scientist might report. The magnitude is equal to the log of I, which is the intensity, divided by S, and S stands for a standard earthquake to which all earthquakes are applied. So it doesn't really matter how large this is. The point is that all the earthquakes are being compared to the same size standard earthquake. Okay, and then therefore the Richter scale is it's logarithmic, but it's a comparative scale. All it tells you is how something is compared to something else, and then a log on top of that as well. It's the I, the intensity, that measures the shaking. So for example, in this problem, how much more intense I, what's the intensity, is an 8.5 magnitude earthquake than a 7.2 earthquake? In other words, if somebody reports an 8.5 and somebody else reports a 7.2, how much more intense is the first earthquake than the second earthquake? So we are going to, first of all, note that in both cases we're given the magnitude, right? This is the magnitude of earthquake 1, and this is the magnitude of earthquake 2. So let's write down, first of all, that we have this. The magnitude of earthquake 1, well, that's defined to be this, right? It's the log of the intensity of earthquake 1 divided by the intensity of the standard earthquake, okay? And the same thing is true with earthquake 2. The magnitude of earthquake 2 is the log of the intensity of earthquake 2 and divided by the same standard earthquake. They're all being compared to the same thing. So you can solve both of these equations for I, because after all, what are we doing? It says how much more intense. That is, we're going to be comparing the intensities, not the magnitudes, but we want to know, hey, how much shakier was the first earthquake than the second earthquake? And that means we're comparing the intensities. So to solve these for intensity, we're going to take the 10, the base, and raise it to the other side of the equation. That is 10 to the m sub 1, so 10 to the first magnitude is equal to I1 divided by S. That's how you solve a logarithmic equation. And likewise for this one, it's going to be 10 to the m2 is equal to I2 divided by S. Now to get I1 and I2 by themselves, we're going to multiply both sides by S. So you're going to get S multiplied by 10 to the m1. That's equal to the first intensity. And then over here, it's going to be S multiplied by 10 to the m2. That's equal to the second intensity. And now they say how much more intense. In other words, it's an issue of comparison. So we're going to take this intensity and divide it by that intensity. And when we do that, we get, let's see, I1 divided by I2. So, you know, what's it going to be? Is this ratio going to be 2? Is the first earthquake twice as intense as the second one? Is it twice as shaky? Is it 3 times as shaky? What does this mean? We're trying to figure out what 8.5 versus 7.2 means in terms of shakiness. Let's see, I1 is S times 10 to the m1, and then we're dividing that by S times 10 to the m2. And what's important here, of course, is that the s's cancel out because they're the same standard earthquake. And we end up with this divided by that, but because they have the same base, we can write it as 10 raised to the m1 take away m2 using the property of exponents. So it's going to be 10 to the, well, m1 is 8.5, and then take away the 7.2 and the exponent, and this is equal to 10 raised to the, well, 1.3. Okay, and that's about equal to, on our calculator, this ends up being about equal to 19.95. Okay, and that would be our answer. In other words, an 8.5 earthquake is almost 20 times more intense, 20 times shakier than a 7.2 earthquake.